Not arrived yet. Or did it go somewhere else? Like, oh, there. Yeah, yeah.
Okay.
Just took a while to come in. There's all this stuff on my screen. Ah, download. Fantastic. So are people free to get their badges now? Can they all come up? Please, please get your badges, please. You can find them. Oh, I didn't. I'm gonna open them and close that. It's fine. I don't want to put in edge. Oh, don't want that. I haven't put you on the website. Do you want to be on the website as head local helper?
Help advertising the.
Yeah, yeah. Well, I don't want to do it. I believe that's we can go big. Well, yeah. Does it just work? Does it not just work? It's not turned on. Maybe need to unplug it and plug it back in again. Not just. Oh! I was going to be like, oh no, it does work. It's fine. Cool. Phew. That's not pointed. That's until they can't really sort of. We can wait for people to arrive and ask if they can hear us.
Yep.
I'm not sure how. We might be getting an owl actually. Todd might be bringing the meeting out, so we won't use this terrible camera. But for now, this is the backup.
Yep.
Oh. You're making a run for it already. Yeah, you're making a run for it already. And I spent too long making those badges, so please.
Mobile stuff. Did you make the mobile?
Yeah. Well, I just like the template.
Yeah.
Well, you put them in the things, I suppose. Okay. So Bruno did help with the manual labor. I did like the skilled part. If anyone would like to pay for the dinner now and have cash, they can come up to me and do it now. It's like, Shanice, do I have £1 coins? Possibly not. This is going to be a bad finish. I have a euro. I will. Well, it's fine. I will have a load of cash, and I will be able to change that to coins somewhere. I hope.
Or this, because everyone's card now.
Everyone's cards.
Yeah.
Oh,
Oh,
Portella's
wow.
got all the coins. It's fantastic.
Well, so I have these because you can't get on the bus with that, right?
I did it this
Well, you
morning.
can use the card. You can use the cards. But this would be very helpful if you have a lot of coins. I will exchange them.
Fantastic.
You managed to do.
I can look at the bar.
We go again. If you would like to pay in cash, I now have change. You can get your change. Oh, my wallet's really thick. Not really too big for my pocket. Look, he's paying for the meal.
I'll get you. Don't worry.
Oh yeah.
I'll write you an IOU.
No, I do not take IOUs. I take cold hard cash.
It's the first thing he said. No, how are you, Nick? How are you?
I don't know. No, Nick, because I met you before. I don't trust you.
Next person's gonna come up to the room and pay like full like copper.
Oh, they're like, no, it's legal tender. Like, no. It's actually.
Oh, yes, yeah.
Some people stand. Pay for a meal, you have to give 40 minutes.
Yeah. Yeah, I feel something I don't know.
Oh, wow, congratulations.
That I expect.
Are you doing?
No, I haven't. Yeah, I'm not sure I'm going.
What is ours?
I am, I'm sorry. It's the thing where I'm supposed to submit for the form back the week before the deadline, so. Yeah. I expect not to.
Hello, what is that?
Thank you.
But there's a plus on that. There's part of this. The manager. Pretty cool. Right here, and then not
The actual writing there is stuff.
You're on the website, local health one. No, they're looking to see it. No.
What time is it? It's 45. I've got ages. I could definitely do that.
Oh, sorry, yeah. Maybe. Yeah, there's one. Still. I would just change that.
When we have these, it's a break, another break.
Yeah. Well, I can still slightly better than if it was just like.
Yeah. Yeah, it's on the right thing.
Very interesting.
Yeah.
Yes, yeah, same. Yeah, having done with it cold and stuff. I have to put myself and so. Yes, no, this is all I don't know quite like how it's found out. Yeah, I mean, it's very cute, yeah, busy when people
No, actually, it's amazing. How do you know? They have.
Well, I think I'm gonna mute it, yeah.
Oh yeah. Also, I should put this on the charge in case it. Do I need to take it out? How does this thing work? Oh, I need someone who knows how this room works. We're not on YouTube. We're not on YouTube for very. How does this thing work? Oh, there we go. Huh? Oh, okay. Oh, it just goes sideways. It goes sideways, obviously. Ah. I was thinking, like, surely it's go in, right? I've seen them in. Is that just kicking there? It feels like I'm gonna break something.
Are you sure you put it the right way around?
Wait, it has. So, somebody is not. Yeah, okay. That's a good point. I'll do that. Oh, thank you.
I've just been on you to figure out who around this. Yep. That's the spare one.
Yeah, I see what's happening. The people who were this. I will do it if you're I'll put the okay, I was good. Wait, I can do it again. It's fine. Wait, no, wait, guys. Okay, good, like, yeah, yeah, but then that's fine. I will reply. Yeah. There's no more. There is just on that side. I gotta see the whole. This is Is that not just how it works? Oh, I see. Well, that was, oh, yeah, I think after the fact, so you want to sell it? No, I think that's good. You should really do something about yeah. If you don't like it, secret. I have a problem with the interface. Yeah, but like. Well, I think that's. Well, like I think wait, that's for a minute. Oh, well, there, it's not, wait, it's not there. So people won't solve it, right? Because you can totally use it now. The way email works is providing body text. If you're around, it doesn't matter. That's not. But it would be good. It's in a lie. I don't want to say what you mean. There's how like we write to each other. These are kind of people we can do no, very soon. It's fine, you're like that. It's not made I think this is why they're also nice. Actually, this is
So they have
yeah, I would have gone that. This is people who have it actually.
Yeah. Yeah.
I'm still debating whether to use it on. So are you expecting, are you expecting to speak for 50 minutes? That's the. I guess in like 45 minutes, I can give you a warning. Oh, I was going to print out a piece of paper with 5 minutes on it, but I didn't do that. Oh well, I'll sort it. That's one, yeah, no buffer or anything, but. Well, I mean, you won't see on the screen. Sure. Oh, there's a clock here. There's a clock right there, actually. Yeah, fantastic.
Do you have slides?
Slides are ready.
Do you want to use one of these? We already have one. It's not later.
Yeah, it does actually.
Mine is a bit better.
Yours is a bit better, it's true. We have both.
That might be slightly confusing.
If someone starts over, I'll throw this line.
Right, we'll 10:09. Start. Take an badge. Oh. It's not loud enough to use my horn. I'll use it yet. It's too quiet for the horn. So I'm gonna do it.
Yours one's out.
Yeah, but that's good. We need the spare. This is good. You haven't gripped mine. You've no idea what gripping is like on mine.
We just go with one that's already connected.
Don't, that's too sensible. We wouldn't do that. No, it's fine. We have one here. What's 11? I'll do it. Oh, it didn't work. Hello. Welcome to SYCO. We're back after a year. I was going to make some sort of joke about how the weather's terrible, but I don't know whether the weather's good or bad now. It keeps changing. It's April, yes, and then what we were expecting. But yes, welcome back to SYCO. It's been a year since the last one. I felt like we should have another one. So I emailed Jamie, waited a long time, and eventually here we are. So yeah, talks on air. Can people online hear me? Doesn't bode well, does it? Do me something. Oh, actually, sorry, yeah. So thanks also to Todd, of course, the co-organizer. Todd didn't help. He is part of the organizing team. But yeah, so some local information. We'll be in here for sort of coffee breaks. There'll be a coffee break a day, and obviously for the talks. Lunch will be up the hill in the CS building, which you may have walked past on the way from the station. What I'm trying to say, if there's a fire alarm, there shouldn't be a test. If there's a fire alarm, go out the door, then turn right and go up the hill to the sort of the assembly point over there. Toilets are just down that way. There's some signs. And yeah, I think that's all I need to say to start off with. So you're our first talk, Miriam. And Miriam will be talking about. Right, to make it full screen. Yeah, screen share. Do that one. Okay. Flow
preserving rewriting in ZX.
Let's see whether we can hide controls. Yes. Cool. So yeah, thanks everyone. Thanks very much for inviting me. It's exciting to be back in Birmingham. And yes, I'm talking about flow preserving rewriting in the ZX calculus. So this is about quantum computing and about graphical languages for quantum computing. And some of the things we want to do with them, some of the difficulties, and the ways that we're overcoming some of those difficulties. So I'm going to kind of introduce you to all of those different terms here, flow preserving, and also the ZX calculus, of course, in this talk. So to start with, am I doing this right?
Yeah. You clicked on the slides. You clicked on the slides.
Okay, yeah, now that's working. Cool. So yeah, so first, I assume most of you do not work in quantum computing, so I'm going to start by giving you a bit of an outline of that. And then I forgot to put in a slide that actually shows you all of the structure of the talk in full detail, but I'm going to wander through various different bits. So first, introduction to quantum computing. Then I'm introducing the ZX calculus, which is the specific formalism for quantum computing that I'm working with. I'm going to be talking about two different models of quantum computing, so two kind of fundamentally different approaches to how to implement quantum computations. One of which is kind of reasonably similar to things that we know from standard classical computing, but the other one is this measurement-based quantum computing model, which is fundamentally different, but gives us kind of interesting ways in which we can think about our computations and our ZX calculus diagrams. And then, yeah, at the end, I'm going to come to this topic of flow preserving rewriting, which is in the title. Oops, that was the wrong direction. Okay. So, yeah, in a nutshell, quantum computing. I'm going to be talking specifically about the quantum mechanics of pure states and qubits. But if that doesn't mean anything to you, don't worry too much about it. So in quantum computing, we describe our qubits as vectors. So everything is kind of linear algebra. And if we're looking at qubits specifically, so at two-level systems, that means our vectors will live in a Hilbert space of dimension 2 to the n, where we have n qubits. So that's the kind of really interesting thing, right? That in the classical world, in order to describe the state of n bits, that's n bits of information that goes linearly, but in the quantum world, it goes exponentially. The transformations that we apply to those qubits are linear maps. And then one of the really interesting aspects of quantum mechanics in general is this idea of measurements. So for our purposes, we're going to model them as projections. But the interesting thing is that they're probabilistic. So we can apply we have a full set of projectors onto all the different parts of our space, but which kind of measurement outcome we actually see is going to be probabilistic depending on the state that we're measuring. And that is something that I'm going to come back to later. in terms of category theory, what we're all here for, we can fix a preferred basis in our Hilbert space, which generally we want to do anyway if we're working on a quantum computer, because we need to agree on which basis we're encoding our data in. And then we can represent our all of our maps in a dagger compact prop. So we are in a symmetric monoidal category where our morphisms are where our objects are just the natural numbers, so the number of qubits that we have, and then the morphisms between them are complex matrices of this exponentially large size, and that allows us to model kind of this pure state quantum mechanics of qubits. But of course, working with these arbitrary exponentially large matrices is not interesting on the theoretical side. Well, it's interesting, but it's difficult. And also on the kind of experimental side, we're not going to be able to directly implement an arbitrary matrix in a physical system. So what we do instead is that we represent everything in terms of some set of generators, so a set of like small operations that we can reason about and work with much more easily, and which we can compose to give us these arbitrary matrices. And so that brings us to the first of our two models of quantum computation, which is the kind of most widely used model called the quantum circuit model. And so in this model, we just kind of say our state preparation, which we have to do at the beginning of the computation, is fairly simple. We just prepare states in our chosen preferred basis. And also the measurements, which we have to do in order to read our data at the end, again, we do those just in our standard basis. And so actually all the interesting stuff we're doing is in the part in the middle, where we just model everything as now reversible, so unitary transformations. And moreover, we're going to pick some set of gates, so some set of unitary transformations that act on just 1 or 2 qubits. Usually, sometimes people have gates that act on more qubits as well. But yeah, we choose them in such a way that we can compose them to get arbitrary linear maps. And then we get something that looks a little bit like this. So here, each of these horizontal wires represents a qubit. And then each of these boxes is a single qubit gate. And these sort of slightly strange operations here, these are 2 qubit gates called control NOT gates. And in this way, we can kind of represent any quantum computation. And in a sense, yeah, these quantum circuits, they're sort of something in between a machine language and just a sort of lingua franca for quantum computing. So they're quite a low-level description of what we're doing in quantum computers. But they're also, widely used from like the very theoretical end of quantum computing, where we're reasoning about computational complexity, all the way to the kind of experimental world where people actually try to implement specific gates as exactly as they can in order to match up with the things that come from the theory side. And whether that's actually like the best approach is something that's still being discussed. But it's sort of the thing that we're working with at the moment. You might have mentioned that might have noticed that on the previous slide I mentioned that actually our linear maps that we're interested in quantum computing, they don't just live in an arbitrary prop. It's actually a dagger compact prop. So we have kind of a dagger structure we can have in these circuits as well. So because each of these gates is unitary, so it each has an inverse that we can get by taking a dagger operation, which is the kind of conjugate transpose of the matrix. But this compact structure is not something that kind of is usually represented in quantum circuits. And so that means that quantum circuits are kind of a little bit weaker than what we really could do. And that's one of the advantages of the ZX calculus that I'm going to get to in a couple of slides. But first, let's talk a little bit more about quantum computing in general. So what are the sorts of questions that we're interested in quantum computing at the moment? So right now on the experimental side, we're sort of at the very beginning of the so-called NISQ era, which stands for noisy intermediate scale quantum. So the idea is that our quantum processors at this point have up to a few hundred qubits, which is just about enough to be able to do things that we cannot simulate even on a classical supercomputer. But it's still far too little to be able to do quantum error correction. So because our quantum operations are described by continuously varying parameters, we need to do error correction if we want to be able to do universal kind of general purpose quantum computing. But that's not something that we're able to do on these NIST devices, because the assumption is that under sort of reasonably realistic assumptions about the error rates on our qubits, we're probably going to need at least on the order of 1,000 physical qubits to represent one logical qubit. So if we've only got a few hundred physical qubits, that doesn't work. So we have to find other ways of tolerating and working around noise, which of course means that we want to keep our computations as short as possible. So that's going to be one of the motivating ideas for this talk. Another thing which I'm not really going to go into here very much is the idea that our current physically existing quantum computers generally have quite limited connectivity in terms of multi-qubit gates. And so again, that's something that we need to be aware of and careful of. So we can't just, in our quantum circuit, kind of put 2-qubit gates between arbitrary pairs of qubits. But if we want to be able to use this to actually run it on an existing quantum computer, we're going to need to be aware of which pairs of qubits we can actually apply 2-qubit gates to, and which places we can't apply them directly, but have to instead decompose them into sequences that make use of the connectivity that we have. So in the longer term, we expect to eventually have large-scale quantum computers that are big enough that we can do error correction. And then that kind of brings with it a different set of challenges, because the error correction schemes that we have don't allow any universal gate sets to be directly implemented in a full tolerant way. So instead, we need to do kind of quite intricate things in order to be able to do universal computation on our encoded states in a way that is resistant to errors. And that means that kind of the computations, the gates that we can't implement directly are effectively going to be much, much more expensive than the ones that can be implemented directly. And so people are already thinking about this and thinking about, how can we reduce the number of these gates that's going to be much more expensive. Another thing that I'm going to come back to a little bit at the very end is the idea of delegating quantum computations to the cloud. So we expect that quantum computers, at least in the medium term, are going to remain quite expensive. And so we're unlikely to just each of us have one in our pockets. But actually, one of the really interesting things about quantum computing is that we can securely delegate computations to a server in such a way that we ourselves only need like a very small amount of quantum computing capability, preparing some states, doing some simple measurements, and nevertheless can ensure that the server doesn't learn anything about the content of our computation, other than obviously an upper bound on the size of the computation. So that's something really interesting about quantum computing. And I will get back to this a very little bit at the end of my talk. But in this talk, I'm mostly kind of interested with actually sort of this idea of optimization. That's the motivation for the things that I'm doing. So both in the near term, kind of just trying to keep our circuits short and simple, so we can implement them without the noise kind of overrunning our computation. Potentially reducing the number of 2-qubit gates, because we know they're going to be particularly difficult to implement because of these connectivity constraints. And then in the longer run, there's also, there are various other gates that we know might be particularly expensive to implement. And so we're going to want to reduce those numbers. And this is all part kind of larger questions around, the idea of building a quantum compiler, because so far, mostly the computations that actually run on quantum computers are still very handcrafted. And of course, this is not something that is really feasible to continue. And we need to build the sort of compilation stacks that already exist in the classical world. But it's, a very difficult and much more complicated undertaking in quantum computing itself. Okay, so that was my introduction to quantum computing. So now let's look at the ZX calculus. So as I mentioned, that's kind of a different set of generators for representing quantum computations. And it has the advantage of really making use of all the structure that we have in the kind of linear maps that describe our qubits. So the compact aspects of the structure, as well as the, it being a prop. And the ZX calculus consists of, again, it's a diagrammatic language, and it consists of 2 kind of main generators. This one's called the green spider, and it represents just a big matrix. The size depends on the number of input legs on the left or output legs on the right. And it's zeros everywhere except in the top right corner, sorry, top left corner, we've got a 1, and in the top bottom right corner, we've got e to the I alpha, where alpha is this parameter in the spider, which is called the phase. And then we've also got these yellow boxes called Hadamard nodes, which represent Hadamard gates that are also used in the quantum circuits. They map between two different bases for our qubits. And then there's two more generators that people use a lot. There are red spiders, which are just the kind of green spiders, but we've changed the basis, so we've applied Hadamards to all of the legs. And then also sometimes in diagrams, we're going to use a dashed blue line between spiders if we've got an edge with a Hadamard gate on it, just because it keeps the diagram a little bit less cluttered overall. But of course, this is only defined between spiders because it wouldn't be compositional if we kind of allowed it to have dangling edges. Sort of dangling part of the wire. So those are the generators. They allow us to write down arbitrary quantum computations on qubits. But of course, in order to really be able to work with this, it's called a calculus. So we also need some kind of rules that we can use to do computation. And I don't expect you to remember all of these, of course. And it's not even kind of the full rule set that is complete for the universal ZX calculus. But kind of one of the ones that's sort of reasonably easy to remember is the one up here, the so-called spider rule, that tells us that if you've got two spiders of the same color that are connected by at least one leg, so one wire between them, then we can merge those spiders and their phase labels add. And we've got these various other rules that I don't really want to go into in detail. We've also got this rule that says only connectivity matters. So this is kind of comes out of both the underlying Dagger compact structure of our category and various symmetry properties of our generators. And it means that basically we can treat our diagrams as graphs. We don't need to worry about how they're arranged in the plane. As long as the connections are the same, that diagram is going to represent the same linear operator. So these particular rules that I've given here are complete for the so-called stabilizer fragment, which is the part of the ZX calculus where all the phase labels are integer multiples of pi/2. I'm going to come back to that a little bit later. But yeah, if we allow arbitrary phase labels, we just have to add an extra 2 or 3 rules in order to get, again, a complete set of rules that allows us to derive any true equality between two diagrams. And so you can see these kind of completeness results. They're actually, it's been a while since we've had them. And so people have been working with the ZX calculus for a while. And so what we're doing is, in order to be able to make use of these kind of extra structures that the ZX calculus has, which quantum circuits don't, we take our quantum circuit, we translate it into the ZX calculus, and then we can now use our reread rules to simplify the diagram. So here I'm just kind of optimizing it in terms of trying to reduce the number of different operations that appear in this circuit, so we can do a lot of things here. For example, here we've got a lot of spiders of the same color that are all connected to each other. So we can just kind of merge them all into one. And then the diagram looks like this. And we can do some more complicated things that I really don't want to go to in detail, but we can simplify this diagram even further into something that looks like this here. And that's kind of the sort of most simplified form that we can easily get. I should mention that for all these kind of optimization procedures that we do, actually finding kind of the single optimal solution is hard in general. So what we're doing is we're just kind of applying heuristics that get us closer to something good. But yeah, there's no guarantee that we're going to hit the best one. And it might not always work, but in practice, it works pretty well. So you might see that this diagram up here, this still looks sort of fairly like a circuit. Not exactly, but we still have kind of these straight wires where we can see where the qubit wires were. And I guess to some degree we still have those here, but down here we no longer quite have that. And so if we do these optimizations and we optimize things as far as we can, the big problem is that, as I mentioned, kind of quantum circuits are our general language that is used both for implementation and also for a lot of theoretical results. So we kind of, after we've done our optimization, we need to translate back to a quantum circuit so that other people can use these results. But if we want to translate an arbitrary ZX diagram to a quantum circuit, that's known to be number p hard. So that's not something that we can expect to be able to do in general. And this is where these flow properties come in that I mentioned in the title. So kind of to give a bit of an overview just of like the results that I'm talking about here. So we start with our quantum circuit because that's the kind of widely used language. So we've got this original circuit, and we want to find some kind of optimized circuit. So I've put a single dot here, but as I've just explained, there's not generally going to be just a single optimized circuit. We're just applying heuristics to find something that is better than what we started with. And in order to do that, we're going to translate to a ZX diagram. And there's this family of ZX diagrams that are circuit-like. So if we translate a circuit, we naturally get a circuit-like ZX diagram. And if we have a circuit-like diagram, that's also fairly simple to translate back into a circuit. But of course, we want to optimize. And if we just did kind of optimizations that keep us inside the circuit-like part, then we haven't really gained anything from using the ZX calculus. So in general, we expect these optimizations to take us out of the circuit-like structure. But then, we're in trouble because, as I've just mentioned, if we want to translate an arbitrary ZX diagram back into a circuit, that's hard. And that's where this property of flow comes in. So we know that there is a class of ZX diagrams which have a property called flow, which I'm going to explain to you in the next section of the talk what that means. But it's this property. It's easy to check whether a diagram has flow, and we know that if a diagram does have this property, then we can efficiently translate it back into a quantum circuit. So that's why flow preserving rewriting is important, because these circuit-like diagrams, they are a subset of diagrams that have flow. And so if we do our optimization in such a way that we're guaranteed to stay within this part of ZX diagrams that have flow, then we can also efficiently translate back into an optimized circuit. And so, I've talked a lot about this flow. So in the next slides, I'm now actually going to introduce you to what that means. And this property of flow comes from this second model of quantum computation that I mentioned at the beginning, which is called the one-way model. So we've already seen the quantum circuit model earlier, where I told you that what we do is we start by initializing our state in a really simple standard starting state in our standard basis. So that's effectively classical information only. We do our computation by applying a lot of unitary gates. And then at the end, we do a measurement, which again is really standard, doesn't really depend on the computation we've done, and just serves to kind of read out the data. The one-way model works quite differently. So what we do is we prepare a so-called graph state at the beginning, which is an entangled quantum state. So that's really something very non-classical, something that can't be described just in terms of giving individual states to the individual qubits that are involved, but we can only describe it globally. And I'm going to explain a little bit more about why it's called a graph state in a moment. And to some degree, this is still actually independent of the computation. So the size needs to scale with the size of the computation. But if we want to, there are kind of universal graph states that we can use for arbitrary computations, assuming we've got one that's big enough. So really what drives the computation, what distinguishes one algorithm from another, is a sequence of adaptive single qubit measurements that we make on this resource state that we've prepared at the beginning. And that's really something very non-classical, because this relies on the fact that our quantum measurements, I think I might have forgotten to mention this at the beginning, but not only are they probabilistic, they actually change the state that's being measured, which maybe sort of, isn't so surprising if you think about them as projectors. They project into a space, so you get something different out than what you started with. So our measurements change the state, and in this way we can use them to drive the computation. But what's a little bit difficult about this is the fact that our measurements are probabilistic. And of course, in general, we're going to want our computation to be deterministic. And that's where the property of flow comes in. So just kind of, one aside before we move on to flow. So if the goal of our computation is to prepare a state that can then be used for something else, we might need some very simple unitary operations at the end to kind of correct for having seen measurement outcomes that weren't the ones we wanted, ideally. But these are, again, like very, very simple things, and the real power of the computation is in these single qubit measurements here, which is why it's sometimes called, it's called a model of measurement-based quantum computing, yeah, I guess the idea of one way is because these measurements are very much not reversible. So in the quantum circuit model, the main part of the computation is done in this reversible way using unitary gates. But here we do these measurements, which we can't undo once we've performed them. So now how do we get a deterministic computation from probabilistic measurements? I'm sort of trying to straddle here a little bit a line between giving you enough detail that you can hopefully understand what I mean without going deep into all the details of these definitions, which are a bit complicated. In order to kind of determine whether our computation can be done deterministically, we have this, as I mentioned, our resource is a graph state. And this graph state really is very closely related to a standard notion of a graph. So we're given this finite simple graph, which in some way describes the state that we're going to be using in our computation. We're then sort of marking specific subsets of the vertices as inputs and outputs for the computation. So here the inputs are by standard marked with kind of a square around them, and the outputs are marked by having hollow vertices instead of filled in ones. And then also we're going, for each vertex that's measured, so for each vertex that's not an output, we're going to apply a measurement label, which gives a little bit of information about how we're going to measure it. And this is one of those parts where I'm going to stay a little bit hand-wavy because I don't want to go into the complicated detail. But yeah, there's basically sort of different types of measurement we do in this one-way model. We don't allow just arbitrary single qubit measurements, but they all have to come from these kind of 6 families. And we label the graph. I've not actually added the labels here, but we label the graph by assigning one of these families to each of the vertices we're going to measure. And then, so that's the information that we need in order to be able to tell whether that computation can be implemented deterministically. And so if we have this information, we can look for this property of flow. And there's various different variants of this, which again, I don't really want to go into in detail, but the flow consists of 2 things. So we've got a partial order over all the vertices in the graph. So that effectively gives us restrictions on the order in which we need to perform those single qubit measurements. And it gives us correction functions. What I think I haven't yet made clear is that if we measure a qubit, there's always going to be 2 outcomes to our measurement. And so in one of these one-way computations, there's always going to be one preferred outcome, which is the one that we ideally want to see. And if the other outcome happens, the one we don't want, then we apply this correction function in order to figure out how to adapt the future parts of the computation in order to compensate for that. And so, there's a specific set of changes we can make to future measurements that make up for having seen the wrong outcome on the measurement we've just done. And so there's these compatibility conditions about these 2 things. So not every labeled open graph is going to have flow, but we can find a flow again in polynomial time. So that's something that's straightforward to do. Maybe to give you just a little bit more of intuition. So this notion of flow is related to kind of standard notions of flow on graphs, but because it also has this partial order, it's a bit more complicated than that. So kind of if your graph doesn't have a flow in the standard graph theoretic sense, then it's not going to have a flow in this one-way model sense either. Just having a flow in the graph theoretic sense isn't enough for us to be able to do a deterministic computation on it, because there's this partial order that comes into it and a few other conditions that connect the correction function, the measurement labels, and the graph itself. Because so the measurement labels are important because different types of measurements are going to need slightly different ways of correcting them. Okay, so that was hopefully gives you an idea of what it means to have a flow on a labeled open graph. And then these different notions of flow, as I mentioned, there's kind of a few different variants, but together they really characterize exactly what it means to be able to do a deterministic computation in the one-way model. Again, in a sort of somewhat specific sense that I don't really want to go into here. This notion is kind of useful in the way that we want to really be able to implement these computations. So as I discussed earlier, kind of the circuit model is currently the standard way that also people working in experimental quantum computing use. But there are some approaches towards being able to implement computations in this one-way model as well. It does have various advantages. For example, you could get someone else to prepare this entangled graph state for you, and then you yourself just need to be able to do single qubit measurements in order to run the computation. So you don't need to be able to actually do universal set of gates. You just need to be able to do these 6 different types of measurements. And then if someone provides to you this graph state, you can actually run a quantum computation yourself without needing to be able to do all that much in terms of quantum computing capability yourself. The reason it's a little bit difficult to implement all of this experimentally is because in order to kind of figure out what kind of corrections we need to do and what that means for future measurements, how they need to change, we need to do some amount of classical computing before each of the quantum measurements we do. And at the moment, the clock speeds of quantum computers and classical computers are very different, and it's not so easy to kind of transfer information between the two of them. And that means that, like these one-way model computations are currently a little bit more difficult to implement than computations in the circuit model. But we're getting there. People are actively working on being able to implement computations in this setting as well. And in fact, I mentioned earlier this idea of secure delegation to a server in the cloud. That also relies generally on this one-way model, because that really kind of allows you to split a computation into different parts in a much more natural way than the circuit model itself. Cool. So that was like a very quick trip through this one-way model of quantum computing. Now, what does that mean for the ZX calculus, which is what we're actually wanting to work with? So there is a class of diagrams in the ZX calculus which kind of quite naturally correspond to these labeled open graphs on which flow is defined. So if we take a diagram that consists of a so-called graph state diagram, which is just a diagram of green spiders connected by Hadamard edges, and each green spider has a single output wire attached to it. And then we add some input wires to some of our spiders as well. So here we've added 1, 2, 3 inputs. And then we add some measurement effects to some of the outputs. So that just means we plug them into a specific set of either spiders or like very, very simple diagrams consisting of two connected spiders. Then this effectively contains all of the same information as the labeled open graphs we just talked about on the previous slide. So the graph state diagram gives us the graph. The input wires kind of tell us which of these spiders are meant to correspond to inputs. The measurement effects tell us about the measurement labels. And then the remaining output wires, which aren't connected to measurement effects, those tell us which of our spiders are outputs. And so what's more important, we can also actually take an arbitrary ZX diagram and we can efficiently bring it into this form, where everything is just kind of green spiders connected in these very specific ways. And then it makes sense. Given the diagram in this NDQC form, we can talk about whether this diagram has flow or not, because there's this natural correspondence to labeled open graphs. And so in the rest of this talk, I'm going to always be working with these MBQC form ZX diagrams where we can talk about, does it have flow? Does it not have flow? And just to kind of talk a little bit about how we can actually translate a diagram back into a circuit if it is an MBQC diagram with flow. It's quite a sort of neat algorithm. So we've got our diagram with flow on this side. So I've stolen this from an existing paper, which is why it says extended G flow. So that's a specific type of flow, but it really works in a similar way for all the different kinds of flow that we have. And on the right-hand side, where we have a circuit-like diagram. So that's something it's still written in the ZX calculus, but it very much looks like a quantum circuit already. And it's very easy to translate into a quantum circuit. And so by doing specific operations on kind of this so-called frontier layer here, the last set of spiders that are connected to the circuit on one side and the MBQC form diagram on the other side, we can slowly transform this diagram into something that looks like a quantum circuit. And interestingly, we don't actually need to compute the flow in order to be able to do this. We just need to know that there is a flow in order to guarantee that this process is going to work out. Right. So yeah, that's now brings us to the last part of the talk, which is talking about this notion of flow preserving rewriting. So we had a look at kind of a set of general ZX calculus rewrite rules at the beginning. But that, for example, involves things like the spider rule, which allows us to either take two adjacent green spiders and merge them into one, or I guess in the other direction, take one spider and split it into two. And so that clearly doesn't preserve this MBQC form, because it would introduce kind of a normal edge between two green spiders. And in an MBQC form diagram, we want all of our edges between spiders in the graph state to be Hadamard edges. So if we want to be able to just do rewriting and optimization in such a way that we always preserve this MBQC form, we're going to need to find kind of an alternative set of rewrite rules for the ZX calculus. So we started looking at that. And one of the sort of interesting things about looking at flow preserving rewrite rules is that in general, we're used to, well, we call them rewrite rules in the ZX calculus, but really they're just kind of axioms. We can use them in either direction and usually do. But if we want to preserve flow, we actually do generally need to treat the two directions of a rule separately. Just because it preserves flow in one direction doesn't mean that it's always going to preserve flow if we're going to go in the opposite direction. Yeah, that's something I found quite interesting. And actually, it was something that's kind of confused a lot of people when we started out working in this area. So yeah, again, kind of the details of this rule that don't matter too much, but yeah, here basically we've got a set of spiders in our graph state. I've not drawn the measurement effects here. I've just kind of, this is sort of a dangling wire that's meant to have a measurement effect attached to it, and then here these also each have kind of a measurement effect attached to them somewhere. And a local complementation consists of two things. So we've got our kind of central vertex here, which is the one about which we do the local complementation. And what that does is it flips all the edges among the neighbors of our central vertex. So here, the top two vertices are originally connected by an edge. So we take that edge away. Whereas, oh, sorry, this edge should have disappeared because it's here on one side, it shouldn't be there on the other side. But like here on this side, we can see there's no edge to start with, and so we introduce an edge. So that's kind of a purely graph theoretic operation, which is sometimes also called, well, it's called local complementation. It's where this name comes from. But in the ZX calculus, in order to ensure that overall our diagram still represents the same linear operator, we need to do a little bit more. We need to add these extra spiders with phases as well. So a red one minus pi by 2 on the central vertex, and then green plus pi by 2s on the spiders all around it. And so that now looks like it's sort of breaking our MBQC form again. But actually what we can do with these things, we can just absorb them into the measurement effect that's connected to each of these things. And then we've got something back that is in this MBQC form. And so this rule is considered to be a rule that preserves the MBQC form. And it's been proved to also preserve flow properties. And in this case, we don't actually need to prove it in both directions, because if we apply this rule 4 times in a row, then we get kind of 4 times pi by 2 on each of these spiders, but 2 pi, 4 times pi by 2 is 2 pi, which is the same as 0, because our phases go into the exponent of an e to the I something. And similarly, if we kind of toggle these edges 4 times, that's again kind of doing it twice actually brings us back to how it was before. So this rule is kind of applying it 3 times as the inverse of doing it just once. But for our second rule on this page, that actually we did need to treat separately for the 2 different directions. So this is called Z deletion in one direction, Z insertion in the other, because this specific kind of measurement effect is called Z. And so here we've got a vertex in our graph which has this measurement label Z, which in the ZX calculus is represented by having a measurement effect that's either labeled with pi or 0. And so we can remove that. We can remove all the edges that were incident on this. We apply these face labels to all the surrounding spiders. And again, we can just merge them with those measurement effects. And that is the Z deletion step. But we can, in fact, go in the opposite direction as well. We can take kind of an arbitrary diagram like this and just introduce a new Z measurement, connected that to all of our chosen set of vertices. And in this case, depending on which version of flow we're working with, we might need to be a little bit careful, but certainly in the kind of most general version of flow, this like inserting a Z does also preserve the presence of flow. And so the really neat thing about these two rules is that actually, together with Tommy, we showed that if we've got two diagrams in this stabilizer fragment of the ZX calculus that I mentioned earlier, so where all of our phase labels are multiples of pi by 2, then just these 2 or 3, depending on how you count, rules are enough to translate one NDQC form diagram into another. So obviously these rules are quite a bit more complex than the rules that we had initially for the arbitrary ZX calculus. But yeah, I still find it kind of fascinating that just these two or three rules are really enough. So yeah, just for comparison, I've put the standard rules back in here. So yeah, like each individual rule here is simpler. I mean, some of them are still families of where we can have arbitrarily many inputs or outputs. But actually, even those we could, in theory, break down into something something simpler and finite. But nevertheless, yeah, we still got kind of 1, 2, 3, 9 rules here if we count the connectivity rule as one. Whereas here we've only got 2 or 3, depending on how we count it. So those are the rules that are enough to do everything we want to do within this stabilizer fragment. But even in the kind of generic ZX calculus, we found that the rules that are complete for the stabilizer fragment are not complete once we allow other kinds of phase labels as well. And of course, the same is true in this MBQC form, flow preserving rewriting. So we're still working on kind of finding a complete set of flow preserving rewrite rules, but we do know that there's kind of various other rules that we can come up with and introduce. So for example, we can take this spider rule and we can make a flow preserving version of that, which looks like this. So this goes in the other direction to the spider rule we had on the previous page. So we're taking a single spider here, the way I've written it, and we split it into 2. And because we're not allowed to have a single like plain wire between 2 spiders in our MBQC form, we instead have to kind of subdivide the edge here so that we can turn it into two Hadamard edges, because 2 Hadamards together are just the same as a plain wire. And then again, we're not allowed to just have 2 Hadamards next to each other in an MBQC form diagram, so we have to insert an extra spider between them. And then that needs a measurement effect, which I've labeled by 0 here. So yeah, so having a spider labeled 0 is actually just the same as having a spider without a label. I should have mentioned that earlier. So yeah, so this rule, again, it seems sort of fairly simple. Again, we need to be a little bit careful with kind of which versions of flow we're working with when we apply this rule. So in the kind of most general version of flow, that's always preserved, even if we go in the direction where we kind of introduce extra spiders. But if we want to work with more restricted versions of flow, then that might not always be preserved, unless we kind of pick and choose quite carefully how we apply this rule. But certainly going in the direction where we kind of take 3 spiders and we join them into 1, again, that basically always works. So now to kind of just talk about some of the applications of doing this. So as I mentioned at the very beginning, if we're working in the sort of longer term when we expect to be working in quantum error correction, we expect that in particular the non-stabilizer operations are going to be much more costly to implement for kind of a broad class of error correcting codes. And so we want to be able to reduce the number of non-stabilizer operations in our computation. And yeah, that's something that we've been quite successful with using the ZX calculus. And in particular, depending on exactly how we want to do this, in many cases, just the stabilizer rewrite rules are already sufficient for kind of getting to something that's quite close to minimal. It depends on, as I said, it depends on how we set it up. In the general case, this is still a hard problem, but if we kind of treat each non-stabilizer operation as a black box with kind of a phase that appears only a single time in our diagram, then all the rewriting we're going to do is basically just stabilizer rewriting plus a very little bit extra. And that's quite interesting because this stabilizer fragment of quantum computing is actually efficiently simulable on a classical computer. And that means that we can actually do all of this reasoning quite efficiently, and everything's just much nicer and more straightforward than if we were working with kind of a more universal set of rules. Kind of in the more near term, as I've mentioned earlier, we might want to reduce the number of 2-qubit gates that we have, because in NISQ devices, so in these near-term noisy intermediate scale ones, 2-qubit gates, we can't apply them wherever we want, and also they tend to have larger errors. And so if we want to kind of at least try and keep the errors as low as possible, having a small number of 2-qubit gates is one way to go. And so in this case, the vertex splitting rule that I just introduced on the previous slide is really useful. That can be applied in order to kind of change our diagram in such a way that we end up with fewer 2-qubit gates in the long run. And then, as I mentioned, there's this sort of really neat secure delegated computation scheme in quantum computing, which is really based on this measurement-based, this one-way model. In general, again, there's sort of different ways one can approach it. Sort of standard proofs have usually used kind of these universal resource states for a measurement-based computation. But of course, using a universal resource means that for any given computation, you're probably actually going to waste quite a lot of the resource because you just kind of cut it out of your computation. You don't really need it, don't really use it for anything interesting. And so there's been some work that's using these flow-preserving ZX calculus rewriting rules that shows that actually in many cases we can kind of really tailor the resource state we use a lot more to the specific computation we want to run without actually losing any of those security properties that we want. Yeah, and that is the end of my talk. So to summarize, I've talked about how we use the ZX calculus to optimize quantum computations. And so translating a quantum circuit diagram, which is the kind of widely used language for quantum computations, into the ZX calculus is easy, but translating an arbitrary ZX diagram back into a quantum circuit is hard. But if we go to this kind of more restricted setting where we only look at MBQC form ZX diagrams that have one of these flow properties, then we can do our translation efficiently. And therefore, we're looking at rewrite rules that preserve this property of being an MBQC form and having flow. And I've talked a little bit about applications in optimization and also in security and obfuscation. So in the longer run, there's some more work to be done around the different types of flow. I've really not talked about these in this talk. But there's kind of different types of flow in specific situations that can be more useful to work with a more restricted version. But a lot of our proofs currently kind of only work for the most general version. And if we want to apply them to these more restricted versions, there's going to need to be side conditions. And we're currently kind of looking at trying to figure those out. There's also kind of two sort of sister languages to the ZX calculus called the W and ZH that have slightly different sets of generators. It would be really interesting to see whether there's sort of similar things we can do with those. It's not at all obvious whether that's possible because this one-way model is really something that works very well in the specific framework of graph states, which are really useful to represent in the ZX calculus. But in a more general scenario, particularly for the sorts of states that are natural to represent in ZW or ZH, not very much is known. And so there isn't so much of a sort of resource of information to draw on. And of course, in general, I've not actually put it on here. We're looking for a complete set of flow-preserving rewrite rules. That was the end of my talk. Thanks very much for your attention.
what was the back? The back when they turn on. Well, if you say the question, maybe you can repeat the question.
Okay, yep.
I have two questions, but I'll start with a short question. So the slide where you have the, I think we call it the Z deletion rule.
Yeah.
You were talking about these flow preserving rewrite rules, but then you said that they don't preserve flow in both directions necessarily. That you've written them as equations, and you've stated a theorem which says that you can rewrite from one diagram to another in this fragment of the next.
Yeah, so if we use the most general version of flow, then they do preserve that in both directions. Yeah, so that's kind of, yeah, maybe where my hand waving is coming to bite me, because yeah, like, so if we work in this most general version of flow, which is called Pauli flow, then they preserve that in both directions. It's only if you want to work in a more restricted fragment that then, yeah, things might break. But yeah, so I should, if I'd written Pauli flow here, which is written in the paper, then then it would be strictly correct. Yeah.
Any other questions first, I guess? Yeah.
Yeah, so when you compare these two models of computation, one way and standard circuit based, I just wonder if one way can be considered just as the software layer over circuit based. So can you actually implement it? Because everything seems already available in circuit model.
Yeah, so the question is about the differences between the one-way and the circuit model, and whether we could kind of consider the one-way model as just a software layer over the circuit model. So in theory, we could, although sort of the way that I introduced the circuit model, partly I was particularly strict in introducing it to kind of contrast the two things. But yeah, so if you allow yourself intermediate measurements in the circuit model, then that allows you to effectively do a measurement-based computation in your circuit model as well. But I think certainly the way that it's used currently is that generally in the circuit model, people will postpone all the measurements until the end because of this difficulty that I mentioned around communication between the classical and the quantum processes. And if you want to just do all the measurements at the end, then you can't do that you can't do with the one-way model. The one-way model, really, you have to do the measurements, not necessarily one at a time, but there has to be that time order that comes from the flow property, that's that partial order that I mentioned. And so really, like, if two things are comparable in the partial order, then you can't do them at the same time. Otherwise, your computation is not going to be deterministic.
Yeah, I think I got it working now. I think I had it on mute. I'm trying to run around the room. Try that. Hold it quite close to your mouth.
Hi. Do you know if other rewrite rules like pivoting or some spiderness identities preserve flow?
Yeah, pivoting does preserve flow, because pivoting is basically just a sequence of local complementations. Yeah, so that's why I haven't mentioned it separately, because yeah, like there's this rule called pivoting, which basically you pick two vertices that are adjacent to each other, and then you do a local complementation on the first, a local complementation on the second, and a third local complementation on the first, and that is a pivot. And so therefore, yeah, it follows directly from this local complementation rule. It has some slightly different, slightly nicer properties than local complementation. So yeah, it definitely is an advantage sometimes to consider it a rule in its own right. But it does follow from this one. And spiderness identities, I don't think anyone has looked at them directly yet. They're sort of related to a generalization of this Z deletion, Z insertion rule, because basically, yeah, this Z thing is related to something like, if we, rather than having just a phase that's a multiple of pi here, if we instead allow an arbitrary phase, then this is what's called a phase gadget. And these spiderness rules, they involve certain combinations of phase gadgets, which together kind of implement the identity. Yeah, so that's something that is actively being looked at. So there's actually I had an intern last summer who was working on this in kind of certain restricted settings. For example, he showed that in the setting of causal flow, which is the kind of the most restricted version of flow, which is almost being a circuit effectively. In that setting, he worked out exactly under what conditions you can insert phase gadgets. and still have flow. Again, deleting phase gadgets is, you can always do that and preserve flow, but if you want to insert phase gadgets, you have to be quite careful under what conditions you do that. So that's something we know for causal flow. He's managed to make a little bit of progress also for the G-flow setting, but it's not known in the general case for G-flow yet. So that's definitely something that's kind of being looked at, but we're not quite there yet.
Back to Nick.
Thanks. So you mentioned that the circuit synthesis problem for ZX calculus in the general case is counting p hard. Now, if you only cared about optimizing quantum circuits, you don't necessarily, it could be the case that maybe it is counting p hard in general, but there are heuristic ways in which you can do a circuit synthesis that might be very fast, which is analogous to how when you optimize the ZX calculus diagram anyway, that's sort of a heuristic process. So if you cared about optimizing a quantum circuit, that could be a valid strategy. So is there lots of evidence to suggest that your approach is fundamentally better than that with this flow preserving rewrites?
That's a good question. I don't think people have looked very much at heuristic ways of extracting circuits because this flow preserving version is just quite neat, and it gives us kind of extra. We also learn a lot of stuff about the one-way model, which in some cases hadn't been known yet. So actually, people knew that flow is important in the one-way model because it gives us determinism, but no one had actually yet found an efficient way of getting translating a one-way model computation into a circuit in the general case until kind of this research direction started in the ZX calculus. So kind of there is that extra interest in we're learning kind of things about the one-way model as well. But that's definitely like sort of looking at heuristic circuit extraction would definitely also be something kind of interesting to do in the broader case.
I guess I was more thinking about with linear programming, the simplex method has an exponential worst case, but it is often the fastest thing to do in practice. And I was wondering if this counting p hard synthesis algorithm might be something like that, or is it definitely not?
Yeah, no, I don't think anyone's looked at kind of average case hardness for that. So I mean, generally, I guess, it depends very much on like how you do your optimization as well, I would expect, because you'd need to do operations that break flow. And I guess if in your optimization you only kind of do a few steps that kind of move you away from the flow, then probably you can still kind of figure out how to get back to it at the end. But in the general case, the further away you get from something that has flow, the harder it's going to be.
It definitely is a practical problem.
I expect so, yeah.
Okay, thank you.
Anything else? Well, in that case,
The question is, if I understood right, to having a flow is a good property. So I just wonder if there are any use of the scenario without flow. Is there any use, or could be eliminated ideally altogether from everywhere?
As I was kind of just discussing with the previous person who asked the question, I mean that there might be optimizations we can do that will get us out of this setting of having flow. And if we really want to kind of, if our goal is to get as close as possible to sort of an optimal diagram, then yes, that might involve leaving this space of diagrams to have flow. I don't think anyone has kind of looked at sort of what effect this would have on kind of specific metrics of interest. That's maybe also kind of an interesting research direction to really look at, sort of compare if we strictly stay within the flow setting, what kind of optimizations do we achieve? If we allow ourselves to leave that, what optimizations do we achieve? And like, what is the cost in terms of, the number of cases where we realize we can't actually get a circuit back at the end. But again, I don't think that's actually been looked at so far.
Okay, so we thank Miriam again. And then as a good segue, we're now Yeah. I believe that's the only just check photos. Control, begin. Work. Yes, so fun. So you just up and down all the drop, right? Again. Sorry, I wasn't done. Really?
All right.
I know. How do I pronounce your name? Sorry.
Alexei?
Alexei. What's your surname? Stop.
Oh, Lisit.
Lisitsa. I'll try my hardest. Someone sound. Yeah. The sound. Who's that? Anyway, right. So thank you for that. So our next talk will be Alexei Sitsa, I think, about automated reasoning for tangles with quantum verification applications.
Right, so thank you very much. So thank you very much for the opportunity to speak here. Very first time at this series of conferences. I always looked with great interest what the people are doing here. So the first time I'm here, I hope to learn a lot of interesting stuff. I'm going to report of our joint work with Andrew Fish, my colleague at the University of Liverpool, and I noticed he already connected online before previous sessions, so he probably also will be available for the comments or answers for questions. Right, so here is the outline of my talk. I will start with a short overview of origins, where it's come from, then we'll discuss a bunch of different concepts from topology, algebra, and automated reasoning. And then we'll demonstrate a few examples of methodology being developed in this research. Now, for origin, I would like just to refer to several papers, just to give a short explanation. So with Andrew, we started exploration of automated reasoning for establishing property of knotted objects, in particular knots, quite a while ago. And in particular, a quite surprising development was that in standard questions in computational topology, for example, given two knots, whether they're equivalent or isotopic, whether you can transform one to another one, or whether you can, given a knot, transform it to something simple, a knot circle, you can actually handle this type of questions very efficiently by standard generic automated reasoning. First order theorem proving or first order theorem disproving. And I mentioned also here the second paper, which mostly, well, I mentioned only two papers. First was mostly focusing on proving, and another one on disproving. Okay, so that was the story on our side and wasn't linked with tangles of quantum programs until we learned about this nice paper by David Werther and Jenny Vickery, who proposed to use tangles, topological objects, for the design and verification of quantum circuits. And the idea here is very nice. So given two quantum circuits or quantum circuit and specification of a quantum circuit, one can associate abstracted version of these objects, namely tangles, and then a natural topological equivalence of tangles do correspond natural equivalence of quantum circuits. So that was proposed as a way of verification. And one particular advantage here is that you can do visual proofs, namely given one tangle, we will see now in a moment, given another tangle, you can visually basically transform one to another one, and by that to demonstrate equivalence of quantum circuits. So that was history before we started the work reported here. So we thought it wouldn't be a nice idea to apply this automated reasoning to a type of questions asked by Werther and Vickery, and this nice paper on verification of quantum programs. And here is our partial response. This is ongoing work. We have more questions than answers as yet, but we believe there is some hope in application of automated reasoning for this type of question. Now, let me start with tangles. So what the tangle is? So you see here, it's just a picture, or one can say a diagram, or two-dimensional projection of, in general, three-dimensional object, which consists of several threads. Or kind of in topological terms, we are talking about generic immersion of a union or a finite number of unit intervals. So each of these threads can be seen as just embedding unit interval into the three-dimensional space. Now, additionally, in general, for the type of applications considered in RV19 paper, it's also needed to add here closed circles as well, probably untangled in an arbitrary way with such a picture. But for the purpose of presentation here, I ignore this version with closed curves attached as well. Now we consider ordered tangles here and oriented and ordered. It's a two close but different concepts. So oriented, it means effectively for each of these thread, you should point out where the start, where the finish. You start from this end, and you go through the thread and finish to another end. This is a oriented tangle diagram, and then we are interested also in ordered tangle diagram. It means essentially the order in which we see the ends here of the diagram is important. And strictly speaking, we have to talk about circular order. To imagine a circle as a boundary of a disk, and all ends, which you see here, three ends attached to this boundary. So then it's important in which circular order they appear. So we are not allowed just to swap them. If we swap them in order, then effectively we get non-equivalent oriented and ordered tangle. And natural topological concept of isotopy, natural equivalence appear, which again should take into account the order of ends. So you can imagine we are allowed to do arbitrary transformation without actually crossing one thread with another thread, but also not changing of circular order of ends. So this kind of transformations lead to the natural equivalence of such objects, and that's what we are interested here to address from automated reasoning perspective. Right, so how do we do that? Well, as before, to do automated reasoning, especially for further theorem proving, we need something less topological, more algebraic. And so here we introduce involutory condols, quite a classical object in topology. And we introduce it here also in these nice diagrams, which probably would be known to anybody who looked at the knot theory. This is effectively Reidemeister moves, so which basically shows some transformation, generally transformation over knot diagrams, but also tangle diagrams I just discussed in the previous slide. So what we see here, so on the left is a simple transformation. So if you have a loop, you're allowed to remove it, or other way around, to create a loop. Then you have Reidemeister type 2 rule. You're allowed to move one of these threads out from another one. And probably most complicated, Reidemeister rule 3, which we have like that, but also intuitively clear. Then now if you consider this indeed as a tangle, just small elementary tangle, we fix the ends. That's type of rules which are quite natural, type of continuous transformation. You just take this thread and move it over this crossing. So it's quite natural topological equivalence here. But what's important here, we can try to encode it as in algebraic way. So effectively, involutory condols is algebraic structure which encodes these things very naturally. Well, I hope these illustrations are self-explanatory.
What's the star operation? How do you say in a capital word star operation?
Star operation. Okay, so from topological perspective, you can see one thread. Okay, sorry. One thread coming X, coming to the another or we say one arc x coming to another arc y and going under. So we consider them as a kind of multiplication rule. So if we have a, this is my x, this is my y, by application of this operation to x and y, I get an arc which is going from another side. So effectively, kind of direct algebraic reading of this very clear topological situation. Arc going under another arc and appear from another side as a third arc. X times y results x times y. Yes?
Are you unable to distinguish in this algebraic representation between the wire x not tangled next to the wire y and just the wire x on its own? Because it seems like the left-hand side of the second Reidemeister move is represented just with an x and here.
Oh, you mean to distinguish this and this situation?
The left-hand side of R2 is indistinguishable and algebraic one from the left-hand side of R1. Is that right? Because they're both represented by an x.
Yes.
So you don't have the information that you have the y wire at all.
No information at all. So it's not information about just the separate arcs. It's about arcs composed into a structure like a tangle or a knot, if we would also close the ends here. So of course this is kind of analogy, but only analogy. So you have to be careful. Yes. Yes, so we have these structures. Now and I would say now just short remark concerning the region of involutory quandles and in general quandles, a variant of this structure, were in a setting of knots and links when you don't have a free ends. But in tangles, we need to deal with the free ends. So we need somehow to provide interpretation for the tangle, strictly speaking. So in order to get a kind of nicer algebraic image of tangles with the free ends, we introduce a concept so-called pointed involutory quandle, which effectively a quandle with a sequence of distinguished elements, A1, AN. So you have just quandle and you actually need to point out some elements. And we also will be interested and also will capture syntactically and deductively the concept of strongly isomorphic involutory quandles. Well, in general, so here is just generic two quandles with arbitrary number of pointed elements, but they're strongly isomorphic only if we have exactly the same elements, literally, graphically, A1, AN, AB1, BM should be exactly the same sequence of pointed elements. And there is also isomorphism of a first quandle to another quandle, such that indeed its identity on these elements. So I would say from a semantical perspective, it's quite strong concept, but it's nicely fit into syntactical side, which we will see just in a few slides time. Now, but before we go there, now we would like to associate with arbitrary tangle some presentation of involutory quandles, essentially to associate some set of generators and set of defining relations. And generators, effectively, for that, we need to consider tangle with a coloring. So when given a tangle, I given some coloring, namely association of some element of set S, then we can associate quandle presentation in a natural way. So effectively, whenever we have a crossing, and we have associated labels, we need just to write this as defining relations, AY, AJ equals AK, according to quandle rule. Effectively, it means if I have some arc going uncrossing another arc labeled A1, going undercrossing arc labeled AJ, so on another side, it should appear AK. So we have to set up this as equalities, again, given some coloring, given some coloring. So with any colored tangle, we can associate then Quandl, involutory Quandl presentation. And as usual, in algebra now, this you can consider now Quandls presented by such presentations. And final kind of technical concept which is needed is that we are mostly interested here, and this class of tangles covers all examples from RV19 paper. It's not a tangles. We now have a strict restriction on tangles. We are saying that tangle is end colorable if whenever you're given some colors to the end, all other ends have been already assigned a color as a term built on the constants of this C. So basically saying you color all the ends and then you follow the rules of involutory Quandls relations. And in this way, you then define uniquely all the colors which need to be assigned to the rest. Not all tangles are end colorable. In some cases, it's not enough. You need to add some additional colors not defined yet by the colors assigned to the end. But in all interesting cases, we consider only end colorable tangles. Okay. Okay. Yes. Yeah, so sorry. Yeah. Okay. So it works. Okay. Thank you. So now we would like to link all these mentioned concepts together. So there are kind of two propositions which are kind of at the center of proposed approach. Now, if we consider two, okay, G-pointed Quandls is exactly as a just pointed Quandls with additional requirements that labeled elements are generators. So you can actually generate Quandl Q1 just by using A1, AN. So if we have two G-pointed involutory Quandls, and then they are given by two presentations of just discussed type, then they are strongly isomorphic if and only if this deductive condition holds in both sides. So effectively, you can derive all equality of one presentation from another one, or using just axioms of involutory Quandls and standard rules of first order logic. Or if you like, equation of first order logic, because we don't need more than an equations here. Now, so it should work in both directions. Now, and second proposition here, which links, so the first one links algebra logic, very roughly speaking, the second links topology and algebra. And essentially saying, if you have two tangles, two ordered and end colored tangles, so tangles are given together with the colors, then they are isotopic if and only if corresponding G-pointed involutory Quandls are strongly isomorphic. So effectively, it says, okay, if given two tangles for this end colorable class, you can assign the colors to all ends in one tangle, in another tangle. Then you can derive all other colors, and then you just test that from one set of qualities, you can derive other set of qualities and vice versa. And that would be enough to establish this. Well, okay, so it works only one direction. So if they are isotopic, then that would be the case. If this is violated, one of these deduction condition, derivability conditions is violated, then we can get out of it that tangles are not isotopic. Good, so that links all together, and so we arrive on this picture. It's quite detailed, but effectively now, given the two tangles, Now we can associate this series, which was shown on previous, basically presentations, series which consists just presentation for tangle 1 and tangle 2. And tangle should be given as colored. If they are not given as colored, you just give them ends the same colors, because we are only interested in cases when indeed there is the same number of ends and given order of these ends. So now we can attach a color, the same colors on both tangles. You then generate two series, T1 and T2, and then you try derivability on both sides. So two possibilities in here. We say two variants are possible. One is you would be able to prove derivability, one set of equalities from another set of equalities. This is an indication that isotopy is possible. It's not yet a proof, and exact conditions under which this is proved is of interest. We don't have exact characterization yet, but we use it rather as heuristic assistance in deriving isotopy moves, how to transform one tangle to another tangle. Now, but if we are not able to prove, but we are able to disprove, namely to demonstrate a counter model, that would give a proof that tangles are not isotopic, and then referring back to quantum applications, corresponding circuits are not equivalent. Sorry. So here is just some examples. So finally, after all this long introduction, some examples. So this is an example indeed taken from original RV paper. So the tangle on the left, a tangle on the right is correspondingly represent abstractions of a quantum circuit, a quantum specification. Okay, from human perspective, visual proof here almost obvious, right? So everybody can see if you don't allow to move ends, you allow only to continuously move the rest of the threads and arcs, you can easily get from left to the right. But here, how it looks like in a theorem proving, when we describe conditions for the involutory quantum presentation on the left, you can see here the concrete example in the syntax of prover 9 prover. You have involutory quantum axioms, you have a goals arriving from TR, so we would like to prove these equalities according to one of the propositions before. And now you actually see the proof graph. So this is a nice feature of so-called prover X platform, which effectively embed prover 9 automated programmers for disprover and allow you also to present the proof not in linear manner, but in just proof graphs. But why it's here? Because now you can see how in fact isotopy should go. You see some like instructions or assistance for finding out isotopy, namely, in this axiom, which actually corresponds to a second Reidemeister moves, x times y equals x, applied to receive A equal F result. And it's applied together with H times C equals F. And that effectively point out for such a move, which you take BC, you move it over this AAF. So we both then get BC, B equals C, and A equals F. Yeah, so effectively, by an analysis of such graphs, one can extract a sequence of Reidemeister moves, but largely at the moment, it's a kind of wishful thinking. For concrete examples, we can demonstrate it, but we don't have yet automated procedure for that. You just have a look what depends on what, and that gives you a hint how you actually move these arcs. Let me then maybe switch another example. This is just, there are versions how you encode it here.
I probably switch the same example in different version, but would rather go to something different, and namely to show non-equivalence or non-isotropy of two tangles. So left tangles of here is taken again from a paper verification of quantum circuits. It's quite complicated, well, at least as compared with previous tangle. And what we would like to show that it's not equivalent, not isotopic to the tangle on the right. And tangle on the right is different only by switching one of the crossings. I don't even see. CD, yeah, yes. So you just switch it. So in principle, if you try to apply visual thinking, it's quite clear they shouldn't be equivalent. You shouldn't be able to entangle or transform one to another one without going through the crossings. But now we can establish it by using theorem disproving, namely finding a counter model for this implication. So this set of equalities. So basically, we show that this set of equality doesn't imply this set of equality. And we show it by just finding a counter model, which on itself corresponds, it could be interpreted as a coloring of ends, such that on the left-hand side, you can satisfy all involutory quantum axioms with this multiplication table on the colors, while if you try to do on the right-hand side, you will get contradiction. So you cannot do that. And that is kind of give you a coloring of ends which distinguishes both tangles and which demonstrates they are not topologically equivalent, not isotopic. And then by reference to the quantum verification, so these tangles, should they be obtained as abstractions of two quantum circuits, also would indicate that quantum circuits are not equivalent. Okay, conclusions and future work. So I hope I can show that there is a hope that automated reasoning can assist in establishing isotopy. It can be used to show non-isotopy. And if you take tangles as abstractions of quantum programs, can be used for verification. Well, future works is also quite obvious. We would like to have full automation of our randomized move instruction for proofs. Characterization exactly when proofs guarantee isotopy. Now it's just heuristic guidance. And finally, it's a nice theoretical question. Are finite counter models always sufficient to show non-isotopy? In theory, it could be infinite counter models. We don't know yet, but it seems in all examples we tried, finite counter models always are sufficient. Thank you.
Do you have any questions? So next again, I'll make a move. Sorry. Oops, sorry. Thank you. Nick upload, so yeah, we'll leave Nick for last.
Yeah, thanks for the talk. It's really cool. If you ditch the involution axiom, then does the similar methodology work for like framed tangles?
We haven't tried yet, but it's a very interesting question. But I would also say concerning variation in terms of quandles, of course, we can apply standard quandles, non-involutory quandles, but it would give you more access to information about orientation, I would say relative orientation of different arcs, as whether you're going underneath from left to right or right to left. So we ignore it here in this approach because this approach is kind of ignore orientation, and orientation only kept by the ordering on the end. But this variance of algebraic structures to try, yes, we should do that.
Cool, thanks.
Is it a quick question then?
Yeah, thanks.
It's a quick question. Okay.
Thanks for the talk. I have a quite naive question. Is this problem of checking for isotopy between tangles in some way very similar to unknot recognition? Because I know a couple of years ago there was a quasi-polynomial algorithm discovered for recognizing unknots, and I wonder if that might have relevance to the things that you discussed today.
Yes, it does. Of course, it's a very related problems. Tangle isotopy is simpler because you fix the ends, and you don't allow to move it over the ends. In knots, so I would refer back to our work on knots, right? So, for example, to establish equivalence of knots, if you try to embed this methodology there, it effectively would lead to second-order reasoning because you need a quantifier, so to speak, on all possible labeling. Now, in here, we don't have this problem because we fix the labeling, because we don't allow these ends move to arbitrary. We just fix them as they are, as we see them. And that makes it much, much simpler. And I do believe, even though I don't have a reference, it should be polynomial time doable, at least for limited class of tangles relevant to quantum verification. I have to be careful here.
Actually polynomial or quasi-polynomial?
I would say for this restricted and colorable, it should be polynomial, but it's just my feeling. I don't have a reference, neither is a proof.
Okay. Even though you rely on stat solving, you think it's like a limited enough fragment of stat solving that it would be polynomial?
Yes.
Okay.
But you really need to put this condition and colorability. If you don't this, so basically and colorability means you put some colors, the rest is computed by following rules of quantums. If you get so to speak, cycles in this process, if you can go then and then back and then back, then you get full complexity of knots. Or even links, even more than that.
Great, thank you.
Okay, so that brings us to lunch. So thanks again. So lunch is at the top of the hill, back that way. We have quite a few local people here, so you should get a guide with Tommy and Miriam also knows the way. Paul there, Paris at the back. So follow someone who looks like they know where they're going up the hill to see us. We'll be back here at 1:30, so 13:30. And if you'd like to pay me for the dinner, you can find me at lunchtime. I have changed now. And next up question. This room will not be locked. So yes, thank you. This room will not be locked. So if you value your things, you can leave them here if you want. They might not be here when we get back. I can't make any promises.